Good morning, Earth Science, and hello. This is your guys' first video lecture I've ever done with you guys, so we're going to walk through just a little bit of how these work and just what I expect from you guys and how these kind of function. First off, I did get a haircut, so it's a little bit different. This chapter's on Earth's formation. We're going to talk about how we've gotten from this kind of rocky, waterless planet to now, to today. The nice thing about these videos is as you guys are watching, if you guys need to stop the video anytime and go back and rewrite something or write down something that you missed, please do so. You can go backwards, you can go forwards, just however best works for you to get these notes. All right, so let's jump into this chapter and we're going to talk about geology, we're going to talk about Earth's movement throughout the solar system, we're going to talk about all these things in this chapter. So let's jump right in to 4.1. Which is all about geology. So geology is the study of the planet Earth, its composition, its formation, and how it's changed over time. This GIF up here does a really good job of showing the breakup of what we consider Pangea, more specifically Gondwana, and how this has led to the Earth that we see today. Earth has changed drastically over the years, it has changed immensely, and it continues to change today. So first we need to talk about how did we get our solar system? Because Earth is sitting in a solar system, we have a sun. So how did we get the solar system? And the best kind of hypothesis and theory that we have come up with is the nebular hypothesis, where 4.6 billion years ago we had this very large cloud of dust, and this cloud of dust it was rotating around in space. And as it rotated, it started to pull itself into the middle. Think of like an ice skater or a ballerina where they tuck their arms in and they start to spin really quickly. As this really big ball of glass got smaller, it started to spin faster. It continued to spin and it continued to shrink and it continued to get faster and faster and faster and smaller and smaller and smaller. To continue this thought, most of the material inside of this cloud got pulled to the middle. This compression of all of these things really closely together made the material very hot. Through hydrogen fusion, it got hot enough that hydrogen fusion started happening. Our star, which we call the sun, was born. And he's kind of tucked away in the middle here. But what's this stuff on the outside of this disk? All right, so the planets and planet formation, about 10% of the stuff that didn't get sucked into the sun spread out in a disk around the sun. And if you take my astronomy, we'll talk about why that happened. It's like a frisbee. As that frisbee is spinning in the air, it flattens out. Same thing here. As this mass was spinning and spun faster and faster, it flattened out into these bands. The friction, the electromagnetical and gravitational forces caused this material in these bands to condense into solid particles of ice and rock. As this ice and rock accumulated from a lot of things going on here to bigger shapes, these bigger shapes started to compress, they started to spin on their own, and eventually these condensed masses would become moons and planets. And that's why all the moons in our galaxy rotate, for the most part, most of our moons rotate the same way around their planet, and the planets rotate the same way around the sun, because we're all part of that same accretion disk from that beginning part. So the spinning motion of ice and rock gave Earth its shape, and we're the third object from the sun. We're the third rock from the sun. Earth's shape, what is its shape? You might be tempted to say it's a sphere, but it's something called an oblate sphere. This is a sphere that bulges in the center. And so this is a little bit more dramatized than our planet, but it's this kind of squashed where the equator is bigger around than the poles are. And this is an oblate sphere. So how do we know that the Earth isn't perfectly round? When we take photographs from space, the Earth looks pretty spherical. It looks pretty round. But when we measure weight, we find some interesting things. So remember that weight is the force of gravity as it pulls on an object. The farther from the Earth's center an object is, the heavier it is. An object weighing 195 newtons at the poles weighs, and you can't see it here, but it's 194 newtons at the equator. Which object is closer to the center of the Earth? And the answer is, of course, the poles. The poles are the closer one because they are the ones that weigh less. The poles, there's less mass between the poles and the center of the Earth. It is closer. All right, now we need to talk about Earth's interior. The original surface of planet Earth looked something like this. Before this, it looked like the moon. It had some molten lava. But at this point in time, the Earth is probably the same material all the way through. It's this accumulation and this mass of different types of metals and elements and other things. As Earth is colliding with meteorites, asteroids, comets, all these things that are left over from the creation of the sun, we're getting more energy and more elements added. So as these objects were colliding with Earth, we get this friction occurring. And as objects collide, heat is produced. And as Earth collided with this nickel and this iron and these other elements, the heat from these collisions causes these metals to melt. And now we have this molten elemental rock stuff. Density starts to play a factor here, and density is the amount of mass that occupies a certain volume. Think of a piece of wood is less dense than the same amount of rock. Rock will sink, wood will float. So substances that are denser will sink below lighter substances. This separated out those melted metals by density, with the heavier metals sinking to the bottom and the lighter metals rising to the top. So what this left us with was a core of the Earth, and at the very center of the Earth, the very inner core, was composed of solid iron and nickel. And the reason it's solid is because it has so much weight of everything else pushing down on it that it's compressed to this solid form. The outer core here, it surrounds the inner core, and it's made of melted iron and nickel. And this is a liquid melted iron and nickel. Very, very high heat there that keeps this stuff a liquid. Above that, we have the thickest layer of the Earth, which is the mantle. And the mantle has high amounts of iron, silicon, and magnesium. And we haven't seen silicon and magnesium yet, but these are lighter elements than nickel and iron. The mantle is solid, but because it's at such a high temperature and such a high pressure, it causes it to act kind of like a liquid, kind of like, think of like lava or something like that, where it's a solid, but it's moving kind of liquid-like. As we move towards the outside, we get to the next part, which is the crust. And the crust is a very thin but rigid layer of lighter rocks that is all of Earth's surface. And the crust sits on top of the mantle. There are two kind of parts to this we're going to talk about. The lithosphere is the crust and the uppermost part of the mantle here. And then it floats on a slushy kind of layer of the mantle called the asthenosphere here. And the asthenosphere is much hotter and more molten than the lithosphere here is. We're going to talk about plate boundaries later, but this is a nice kind of convergent plate boundary here, specifically a subduction one, where this one's going underneath of another one. We'll talk about that when we talk about plate tectonics. All right, the heat on Earth. Earth's heat was generated from three things, and they were, the first thing, meteorite impacts. Lots of meteorites that were leftover sun bits were crashing into the Earth, creating heat, creating a lot of friction. The second one was the weight of materials causing compression. As these materials sunk, as this nickel and iron sunk down towards the core, they created a lot of friction as they were going past other very hard metals. They caused this a lot of compression. This caused a lot of heat. And the third thing is the decay of radioactive isotopes. You've all heard of like uranium, which is a radioactive element we use for energy. Things like, there's a ton of radioactive isotopes that exist in Earth's kind of core, mantle, crust, etc. These radioactive elements create a lot of heat. All right, this is the end of chapter 4.1. We're going to start, this video is going to continue right into 4.2. And 4.2 is all about the heat loss of Earth. and some other features of Earth, and specifically Earth itself and the features that it possesses. So, since the beginning, Earth has been losing heat. We've been radiating heat back out to space. So where do we lose heat? Number one, rocks lose heat faster than others. Some rocks lose heat very fast, some hold on to it for a long time. The difference here also is from the thickness of the crust. From place to place, it is thin, the crust is thinner, or the crust is thicker. In the thicker parts, the heat isn't lost as fast. In the thinner parts, the heat is lost very readily. And the third thing is the percentage of radioactive materials varies. There's a different amount of radioactive material in different spots. There's pockets of radioactive material that cause a lot of heat in certain places. Earth possesses a magnetic field. This is why whenever you have a compass, it's always going to point north. This field is not directly in line with the poles. On this diagram up here, the poles are located right here, the geographic South Pole and North Pole, and then the magnetic one is tilted at 11 or 11.5 degrees sideways from it. And this is caused by the movement of liquids in the Earth core. These molten iron and all these other things, they have magnetism to them. Anytime that you have magnetism moving around, it creates an electrical field, which creates a magnetic field. This magnetic field is really good for us. It keeps our atmosphere attached. So we like the magnetic field. We're big fans. All right, Earth's rotation. Now, how long does it take Earth to rotate around its axis? And rotate is that spinning motion. Well, it takes 24 hours. One rotation on Earth is equal to 1 day. We're going to talk about revolutions, and that's Earth moving around the sun. But for right now, we're just talking about the Earth itself spinning. So let's talk about some evidence for this rotation. Jean Foucault, he was a scientist who attached an iron sphere to a really long wire, like a really long wire, like up to 20 stories high here. And as this wire was swinging, every hour it would swap, and it would be going 11 degrees clockwise. After 8 hours, it was at a right angle to its original path of motion here. So what this is telling us is that this thing is swinging back and forth, but it looks like this pendulum is not only swinging back and forth, but moving in this kind of clockwise position. Now the question I have for you is, did the pendulum change its motion? Did the pendulum change its motion? And the answer is no, of course not. What happened was the shift in its direction was because the Earth was turning underneath of it. So the Earth is spinning around, and this pendulum was moving with it, was moving kind of side to side there. Here is an example of a Foucault's pendulum. You can find them in lots of discovery centers and science centers across the nation. They have these little dominoes or little pegs, and every hour or so they will knock down a peg. Every 30 minutes. This one's set for every 30 minutes. It will knock down a peg. All right, some other examples of evidence for Earth's rotation is the Coriolis effect. Winds on the planet Earth do not blow in a straight path. Instead, they say we're deflected, or they are turned. In the northern hemisphere, this deflection is to the right. In the southern hemisphere, this deflection is to the left, towards the equator. This is what we call the Coriolis effect. And when we talk about weather, and we talk about winds, and we talk about tornadoes and hurricanes, the Coriolis effect is going to play a really big role in that. It's going to be really important for that discussion. All right, so let's talk about the Earth's axes and its rate of rotation. Earth does not only rotate around its pole, it also spins around the sun. It orbits around the sun. This line is called an orbital plane. So as the Earth is moving around the sun, this is the line that would cut straight through the middle of it. This is the path that's going through around the sun. Our axis is not perpendicular to that. It does not make a 90-degree angle. Instead, our axis is tilted, and it makes this 23.4 degree angle here. And this is going to be an important number that you're going to see again. So let's talk about measuring Earth's spin. So we know that Earth makes one complete turn, 360 degrees, every 24 hours. That means that each hour, Earth is rotating 15 degrees. 15 degrees per hour. Because Earth is shaped differently, because it's that oblate sphere, it rotates at different speeds. Near the equator, it spins faster, around 1,050 miles per hour, while the poles spin at 0 miles per hour. This is because the poles are the axis of rotation. Because they are right at that spot of rotation, they're not moving, they're not changing their position. As you move further away, as you move down towards the equator, it starts to get faster and faster. This is kind of why, and this kind of explains why, certain polar regions have 24 hours a day daylight during some times of the year and 24 hours of nighttime during the other parts of the year, is because they're not spinning around enough to catch that light. So rotation affects our planet in a lot of ways. And the most obvious effect of rotation, of course, is the daily change between night and day on the planet Earth. We also see in the Coriolis effect, we've talked about it, but without spinning of the Earth around, one side of the Earth would be super, super hot as it would always be getting sunlight, and one side would be frozen as it would be completely stuck in darkness. Only because the Earth spins do we have this really nice heating and cooling of the Earth. I like it hot, but not this hot. If you watch if you go take my astronomy class, we'll talk about measuring time a lot more, but we're going to touch on it just briefly for this class because we're talking about time zones. But early man based time on sun's location. So sun starts in the east. At noon, it's at the highest point in the sky, and it sets in the west, which is evening time. The problem with this became that solar noon, or when that sun is right in the middle of the sky, does not occur at the same time everywhere on the planet. In fact, the sun moves westward at about 15 degrees an hour, or 1 degree every 4 minutes. So to kind of standardize this so that everyone was on the same time, we had to invent time zones. And our standard time zones were created to accurately help us tell time. There's 24 time zones around the world. Each one is 15 degrees of longitude apart. And it's important to note that these meridians are exactly 15 degrees apart. And we call these the time meridians. And these are the areas between meridians that keep the same clock. So in the Pacific zone here, our time meridian goes from Montana over to the coast, which is about 15 degrees of longitude there. Now, the starting point for all these is the prime meridian. This is where we start our standard time zones. And moving west, your clocks will go back to earlier times. So as we start to go west more and more, we get earlier and earlier. Moving east, your clocks go forward to later times. You get later and later. Another really important meridian is the international date line. If you move all the way around the world, you either gain or lose a day. And we call this point the international date line. And it's really convenient that it's out in the middle of nowhere in the Pacific Ocean. We have fudged it a little bit, where we wanted to keep like the country of Russia wanted to stay on the same time. And then we've got a little kind of a dip down here. But instead of changing the clock on this date, you would change your calendar. So if you go west across the line, you go 1 day later. If you go earlier across the line, east across the line, you become 1 day earlier. You would move from the 13th to the 12th, for example. This is the end of 4.2, but we're going to jump right into 4.3, which is talking about Earth's revolution. And revolution is the movement of Earth around the sun. And there's lots of evidence for revolution. The first is that the constellations change seasonally. This is because our location in space is changing, so what we can see in space changes too. A cool kind of example of some Earth's revolution evidence is parallax, and parallax is this really cool feature where nearby stars seem to shift position when you're looking at them compared to distant stars. We can't view the stars very well with our naked eye, so we use instruments to view this instead. However, this is an effect that you can use. I haven't tried it on the Chromebooks, but here we go. This picture here is to show parallax. what I want you to do is I want you to take your thumb and I want you to cover a spire or some kind of structure, a cactus or something on this picture. And then with one eye closed, I want you to close that eye and open the other one. You should be able to see whatever piece of this picture you were covering up should now become uncovered. As you move further and further away, this becomes less and less obvious because you're moving further and further away. Your eyes aren't going side to side so much. But this is some really good example when we look at the constellations and we look at the stars that we are in fact moving. All right, so the path and the rate of revolution. Our revolution direction is the same as our rotation, counterclockwise as viewed from the North Pole. So we're going this way around our sun. This shape, this kind of oval shape is important, and that's our orbit, which is an ellipse. This shape is called an ellipse. And all ellipses have two foci. And for us, the sun is located at one of them. So imagine the sun's right here. Actually, I think it's going to be on the other one, but here we go. Okay, so on our distance from the sun, on average, we're 93 million miles from the sun. 92,960,000 miles from the sun. There are two important points on our trip around the sun that we take note of. And the first is the perihelion, where we're closest to the sun, which for our planet is around January 2nd. And then the aphelion, which is the part farthest from the sun. And this happens around July 4th. Earth orbits the sun every 365.24 days. This is why every 4 years we add up this 2.24 4 times, and now we're at 96.96 days. We add an extra day, which is on the leap year, and we add a leap day. This is to make up for that 365.24 leap day. Oops, excuse me. My pen started to wander there. Leap day, so that's a leap day. All right, some effects of the revolution and the tilt of the Earth. Because the Earth is tilted, the side closest to the sun receives more sun, gets warmer, and has longer days. The hemisphere that's tilted away has shorter, cooler days. So in this one here, the northern hemisphere is the one tilted closer to the sun, so it's getting more sunlight, and they are in summer. The southern hemisphere is pointed away, the sun has to travel further, it cools off, and it becomes winter. It's not how close we are to the sun, but who's tipped closer to the sun at that point in time. If the Earth was perpendicular, if our axis was like this, where we're at a nice right angle, we wouldn't have any seasons. We would have 12 hours of daylight, and we would have 12 hours of darkness. If we had more tilt, if the Earth was something crazy like this instead, we would have hotter summers and colder winters. And so we would have a lot more extreme weather. We would have a lot more droughts, a lot more floods, hurricanes, tornadoes, you name it, we'd have it. So we like that 23.4. That's about that really nice Goldilocks zone on that. All right, so now we need to talk about the solstices. The solstices are a really cool event where in the summer solstice, the northern hemisphere is at maximum tilt towards the sun. So we are perfectly pointed towards the sun as most as we can be. On this day, which was June 21st, this is the longest day of the year. The sun is directly over the 23.5 degrees north latitude on the planet, which we call the Tropic of Cancer. So 23.5 degrees north, Tropic of Cancer. On the first day of summer, which is this day, every line to the north of the 23.5 degree line of latitude has 24 hours of sunlight. So anything 66.5 degrees north or more, which we also refer to as the Arctic Circle. So parts of Alaska, Canada, Greenland, Russia, all of these get that 24-hour cycle of daylight during this time. Now, the winter solstice, on the other hand, which begins on December 21st, is the shortest day of the year. We are the maximum tilt away from the sun. So we are the coldest, we get the least amount of sunlight on that day. The 23.5 degree line south in the southern hemisphere now has the sun directly over it, and it is called the Tropic of Capricorn. They're called these because of the constellations that are over them. Mr. Greer is a Capricorn, in case you were curious. At this date, the Arctic Circle, or that 66 degrees north on the northern hemisphere, gets 24 hours of dark. It's important to note that in the southern hemisphere, these things are reversed. So on the winter solstice in the southern hemisphere, they're getting that 24 hours of daylight in their Arctic Circle down there. So Antarctica is getting 24 hours of daylight at that point in time. Now we've talked about the furthest tilt away and the closest tilt to, but let's talk about what happens if we're right smack dab in the middle. If we're right smack dab in the middle, we have something called an equinox. And this is the days that are halfway between the solstices. The daytime and the nighttime are equal on these days, 12 hours, 12 hours. The vernal equinox is March 21st. And the autumnal equinox in between the summer and winter is September 22nd. So right before we come back to school is we were in school during that for the September 22nd autumnal equinox. At these days, the sun is directly overhead the equator, and it's either moving up towards the 23.5 degrees north or down towards the 25 degrees south, depending on which solstice you're headed towards. This is the conclusion of chapter 4. I hope that you enjoyed this information. You got a lot of information about Earth from this, about kind of the physical structures of Earth, the interior of it, how it rotates around the sun, how we get seasons, how we rotate around our poles, how we have a magnetic field. All this stuff is really good and will kind of lend itself as we continue to talk about geology in the next couple chapters. Thank you for watching and have a great rest of your day.